Hello, everybody. This is Bert Dixon here presenting today on the topic of combinations and probability. So before we start that lesson in the book, I'd like you to consider a couple of problems that might help this lesson make a little bit more sense. So in this first problem, actually, like I have two number ones here. That's interesting. Okay, so there we go. All right, so in number one, we have four people, Tim, Aditya, Roberto, and Naya, and we need them to fill three positions. So we have a president position, a vice president position, and a secretary. So this is president, vice president, and secretary. Okay, so if we want to know how many different ways this can happen, we ask ourselves, how many different people can fill this president position? Well, there are four. And then once we place somebody there, how many people are there that can fill the vice president position? There are three. And then the secretary position, there are two left. And so that would give us 4 times 3 times 2. That would be 24. There are 24 different ways that we can elect a president, vice president, and secretary given only 4 candidates. Okay, if they can all 4 fill any of the 3 positions, then there are going to be 24 different possible outcomes. Okay, this was an example of a permutation. So to put this in the permutation notation, this would be 4 people were permuting 3 of them. And again, if you did that using the formula, that would be 4 factorial over 1 factorial. 4 is 4 minus 3 factorial. And so that is 4 factorial, 1 factorial, which is 24. Okay, now in the next question, we're interested in how many ways can we make a 3-person committee. Okay, we don't have specific positions for them, but how can I just form a committee? Okay, so if I do Tim, Aditya, and Roberto, that's 1 committee. Now if I change their order, Roberto, Tim, and Aditya, that's still the same committee. It's the same 3 people. So the committee is no different. And so we wouldn't consider that a different committee. So we can do Tim, Aditya, and Roberto. Why don't you take a minute, pause your video, and see if you can list all of the different 3-person committees that we could get using these 4 people. Okay, press play when you're ready to check your answer. Okay, so this might be easiest to think about. Who are we leaving out? So the first one we left out Naya, and then if the next combination, let's leave out Roberto. So then our committee would be Tim, Aditya, and Naya. And then the next time we're going to leave out Aditya. So now it's Tim, Roberto, and Naya. And then if we leave Tim out, that would be Aditya, Roberto, and Naya. The order doesn't matter. You can rearrange these letters however you want. If I rearrange these to be NTA, it's still the same 3 people. It's still the same committee because the order doesn't matter. And so the difference between these 2 problems, we still, in problem number 1, we had 3 people and we were putting them in 3 positions. And in example 2, we have 3 people and we have 4 people and we put them in 3 positions. But this answer turned out to be only 4 outcomes, whereas this turned out to be 24. So the difference is that in example 1, the order matters. If I do Tim, Aditya, Roberto, and then Roberto, Tim, Aditya, that's considered a different outcome because in this outcome, Tim is the president, whereas in this outcome, Roberto is the president. And so those would be considered different outcomes. But in this case, I have a committee. The order doesn't matter. So when I change the order of the letters, I get the same committee. So the order doesn't matter. This is an example of a combination, whereas example 1 was a permutation. And again, we've studied permutations already, so you should understand those. In a permutation, the order matters. When I change the order, it's a different permutation. But in a combination, the order does not matter. So when I change the order, it's still the same combination. Okay? So in a combination, oops, sorry, wrong page. In a combination, we have a way of calculating it just like this. This was 4P3. We're going to write 4C3. C stands for combination. And the formula for NCR is n factorial over r factorial n minus r factorial. And so for this one, we would get 4 factorial, 3 factorial, 1 factorial. And so that turns into just 4 if you do that, because we'd have 4 times 3 times 2 times 1 on the top, 3 times 2 times 1 on the bottom, times 1 on the bottom. Those all cancel with those, and we just get 4 as our answer. And so that matches what we did when we did it by hand over here. Okay, so this is the formula for combination. Now, I will say that even though this C really means combination, it makes a lot more sense in a lot of these problems that we do if instead you say choose when you see the letter C instead of combination. This is hard to say even. N items, we're taking combinations of R. That's kind of awkward to say. But if you replace it with choose, which just by a nice coincidence starts with a C as well, it makes a lot more sense, because I can say I have N items, I'm choosing R of them. So let's look back at problem 2. I have a 3-person committee. I have 4 people here. I'm going to choose 3 of them to be on the committee. 4 people, I'm choosing 3 of them to be on the committee. So when you see NCR, think of it as choose instead of combination, and it'll make a lot more sense in the problems that we do. So let's keep that in mind as we do some of these problems in the book. Okay, so let's go ahead into our book in section 21.3. This starts on page 1107. And we can actually skip down to page 1108. You'll see the same formula there that I mentioned a few minutes ago. That's the formula for combinations. And so in example A, we have 4 boys and 8 girls on the debate team. The coach randomly chooses 3 of the students to participate. So we have 12 people. We're going to choose 3 of them to participate in a competition. So 12 choose 3. What is the probability that the coach chooses all 3 girls? And so there are, so this is going to be 12 choose 3 is the number of ways that event A occurs, which means, this would be actually the number of items in the sample space is going to be 12 choose 3. And the number of ways that event A occurs is going to be choosing all girls. There are 8 girls. We're going to choose 3 of them. And so the probability then is going to be, the probability of event A is going to be 8 choose 3 divided by 12 choose 3. And so that is if you do 8 choose 3 in your calculator, by the way, that's in the same place as permutations on your calculator. So if you go to math, probability, actually let's put in the number first. So I'm going to do 8 math probability. There's NCR. So 8 choose 3 is 56. So this is 56. And then 12 choose 3. 12 math probability. Oops. 12 choose 3. 12 choose 3 is 220. And so then if you do 56 divided by 220, you get that that's about 25.45%. Or this also reduces to 14 over 55 as a fraction. So this or this. Okay. So now let's take a look at example B. This time we have a deck of cards, 52 cards in a standard deck of cards. We have 13 cards in each suit. So they're in the suit of clubs, there are 13 clubs. There are 13 diamonds, 13 hearts, and 13 spades. And 5 cards are chosen at random. What is the probability that all 5 cards are diamonds? So the number of items in the sample space is going to be 52 cards. We're going to choose 5 cards. So that's 52 choose 5. The number of ways that event A occurs is that all 5 of the cards are diamonds. So there are 13 diamonds. We're going to choose 5 of them. And so here we have 52 choose 5. And then that is 52 factorial, 5 factorial, 47 factorial. I'm not sure if they want a simplified fraction there. The number of items in our sample space is, or in the number of ways that event A occurs is we have 13 clubs. We're going to choose 5 of them. So then that's 13 factorial, 5 factorial, 8 factorial. And so if we do each of those, 52 choose 5 is 2,598,960. And then I can change that to 13 choose 5. That's 1287. And so now the probability of randomly selecting 5 cards that are diamonds is 1287 over 2,598,960. And that is that number divided by that number. It doesn't want to convert it to a fraction for me. No, it's just giving it to me in scientific notation. So that the textbook says that simplifies to be, our calculator doesn't give it to us, but it's 33 over 66640. You know, an easier way to get that, if we do this, if we write it this way over this, we have 52 factorial over 5 factorial, 47 factorial, and then we're dividing by 13 factorial divided by 5 factorial, 8 factorial. These cancel. So another way to do that would be if you flip and multiply, you get 52 factorial, 8 factorial over 47 factorial 13 factorial. So that might give us some smaller numbers. You can actually cancel the from 52 factorial, that would be 52, 51, 50, 49, 48, 47, 46, and so on all the way down to 1. Well, from 47 down to 1, those are 47 factorial. So all we have left is 52, 51, 50, 49, 48 times 8 factorial over 13 factorial. If you do that on your calculator, it'll be a much smaller number and easier for your calculator to simplify it. 52 times 51 times 50 times 49 times 48 times 8 factorial. Oh, 8 factorial. Let's see. Divided by 13 factorial. 13 factorial. Math frac. There we go. Oh, I did it upside down, but yeah, I had put the wrong piece on top. But so it's giving it to me as 66640 over 33, and that's what we got here. But I just did it upside down. This was supposed to be the other way. Okay, so that gives us the same answer, and then that is 0.000495. Okay. So go ahead and try problem number 4. If you toss a coin 4 times, what's the probability of getting exactly 3 heads? So pause your video, try it out, and press play when you're ready to check the solution. Okay, so this one you might be wondering, how is this related to combinations? So if you do exactly 3 heads, you can have heads, 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 tails, or you can have heads, heads, tails, heads, or you can have heads, tails, heads, heads, or you can have tails, heads, heads, heads. And so we see that the answer is 4, but how is this related to, if there are 4 different ways to do this, then the probability of exactly 3 heads is 1/4. Okay, but how does this relate to the topic we're studying today, which is combinations? If you look at each of these, they each have 3 H's. So we have 4 positions, 1, 2, 3, 4. Which 3 positions am I going to choose to put the H in? And so that is the same as 4, choose 3. We have 4 positions. We're choosing which 3 am I going to put the H in. Okay, so 4, choose 3. If you do that on your calculator, you'll see the answer is 4. Notice that this could also be thought of this way. We have 4 positions. We're choosing which one to put the T in. So you could also think of it as 4, choose 1. Notice if you do that on your calculator, 4 math probability 4 choose 1 is 4, and 4 choose 3 is also 4. And that makes sense that they would give us the same answer, because if we have 4 spaces and we're choosing which 3 to put the H's in, that's the same as choosing which 1 space to put the T in. So 4 choose 3 or 4 choose 1, they both give us the same answer, because this, according to the formula, would be 4 factorial over 3 factorial. The difference between 4 and 3 is 1. So you get that. This one is 4 factorial over 1 factorial. And the difference is 3 factorial. So notice that these are actually the same. Okay, now go ahead and try problem 5. Pause your video and press play when you're ready to check your answer. Okay, so we cut the deck in half, and so we have only red cards now. 4 cards are randomly chosen from the red half. What is the probability that they are all diamonds? So our sample space is going to be, we have 26 cards. We have 26 red cards. We're going to choose 4 of them. So that is 26, choose 4. The number of ways that event A occurs, what's the probability that they're all diamonds? There are 13 diamonds. We're going to choose 4 of them. And so the probability of all diamonds is going to be 13 choose 4 over 26 choose 4. And that is 13 choose 4 is 715. And change that to 26. 26 choose 4 is 14,950. If I do 715 divided by 14,950. Oops. Let's try that again. 715 divided by that math crack is 11 over 230. Which is about 4.8%. Okay, so the next thing we're going to look at is how do you apply this concept of combinations to situations where you have multiple combinations that you need to add together. And so for this one, we're flipping the coin again 5 times. What is the probability that the result of the head is heads at least 4 of the 5 times? So when we say at least 4, that could be 4 or 5. So we have 2 outcomes. We have 5 coins. We're going to choose 4 of them to be heads, or we have all 5 heads. So that would be 5 choose 5. So this is 4 heads. This is 5 heads. And so to get our probability, then we're going to divide that by the total number of outcomes, which is when we flip 5 coins, 2, 2, 2, 2, 2, that's 32. And so they showed here that these 2, which we have on top, together adds up to 6. 6 over 32 is 3/16, or 3 divided by 16 is about 18.75, exactly 18.75%. Okay, so when it says at least, you have to include that number and all the numbers bigger than that. If it said at most, it would be all the numbers leading up to that. Okay, so let's take a look at problem number 7 on page 1111. Okay, so pause your video, try this one out. Press play when you're ready to check the answer. Okay, so the key here is this one says at least 3 girls. So that means 3 girls or 4 girls or 5 girls. So 3 girls would be 5 seniors are randomly selected. What is the probability that they contain at least 3 girls? So out of these 5, we're going to choose 3 of them. Out of the 5, we're going to choose 4 of them. And out of the 5, we're going to choose 5 of them. And so the number of items in our sample space, or in our event A, is 5 choose 3 is 10. 5 choose 4 is 5. 5 choose 5 is 1. So that adds up to 16. Now, how many total possible outcomes are there? Well, if we're choosing 5 seniors, they can be boy or girl. So there's 2, 2, 2, 2, 2, which is 32 again. So this is just like heads or tails. They're boys or girls. And so 16 divided by 32 is 1/2, or 50%. So this gives us our size of our sample space. So the probability of at least 3 girls is 1/2. Okay, that's it for today's lesson. Have a great day, everybody.